Here is our notebook about hybrid search. Let's go over it and see how do we build it, how do we use it. We have the usual visual improvements and the warning suppression. Let's start with the actual sparse index. Here we're going to use a library called BM25S. It's a Python implementation of the BM25 algorithm. We're going to build both the tokenizer, we're going to use a stemmer, we're going to talk about it in a second. We load those Python libraries, and we're going to load the chunks of the documents from the AI archive that we used before, after they were already chunked using semantic chunking and the contextual retrieval and all the magic that we did so far. If you want to create a sparse index, we need a tokenizer. This tokenizer will be slightly different than the tokenizer that we had in our embedding, because here we are searching for words that we know that are common in the documents. Therefore, we're going to use a stemmer. A stemmer will remove s and ing and a few other prefix or suffix that we have in our language. So we have from multiple words, we can have the same word. And we're going to also use stop words, which remove words that we don't care about, like and is and this and things that we don't want to search on. Let's see those words. So here are the words that are built into this library. And R and so on. We can update that and add other words that we know that are in the text and we don't care about. But for now, we're going to use it as it is. And now we're going to calculate the tokens from the corpus text that we have. We're going to build the vocabulary, and we care mostly about those IDs. We're going to create the index using the BM25 in-memory implementation. Remember that most vector databases also have the sparse vector implementation, so you don't have to run it in memory. You can put it alongside the dense vectors. And we're going to generate the index based on the corpus. It's a very quick process. We don't have that many documents here, but nevertheless, this is a fast process because the sparse vectors are sparse and there are not that many tokens to calculate. So let's see what did we get. So we're going to review the vocabulary from the tokenizer. And we'll search one of the words. Again, remember that from our query, we want to know what is the context size in a model. And we're going to focus on the token context. And we're going to search it inside of the vocabulary. And we can see that overall, there are almost 1,700 tokens. And our token is token 127. Remember that the tokenizer encode and decode. So we can also decode back from the 127 and get the word context again. So this is a two-way process. And now let's see how the sparse index looks like. This is an efficient representation of the sparse vectors, an array with all the scores, each token and the document, and some kind of a mapping between the tokens and their documents. If you want to see exactly how we represent a specific token, we're going to focus our token, the word context, as we saw before, and we're going to check the indexes inside of this representation, and we're going to print it out nicely in a table. So let's see how it looks like. So remember, context is 127, and we can see that it appears in those 10 or so documents, document 0, 2, and so on. The most significant document is document 15, when the score of the word context in it is 1.1, but also it appears in 14 in a very close score and so on. So we're going to use those scores. We're going to search for the query. How do we search? Here is a query from the previous notebook. What is the context size of Mixtral? We know that we have documents that talk about that. We're going to tokenize it with the same sparse tokenizer. Remember that if you want to search the sparse index, you need to use the sparse tokenizer. We are not going to update the vocabulary, because if we have new words in the query, we don't want to update the index because the words don't appear in the documents. And we got the 127, which we know is the word context, 128, which is probably the word size, and 15, which is probably the word for Mixtral. The word off and is were removed as a stop words, if you remember the list that we saw. The word what didn't appear in the documents, therefore it's not in the vocabulary, and because we don't update the vocabulary, it doesn't appear here. So we only have 3 tokens, context, size, and Mixtral, and we're going to search it in our index. And as you can see, it's a very, very quick process. The index is small. It's very efficient to search it. We have the top 10 documents. We see that the first document is document ID 2, then 14, then 1, and 15. So we saw those were the documents that were high in the word context, but we also have the word size and mixed trial. So overall, from all the query, they have the higher score for the sparse index. To make it in hybrid, we also need to create a dense index. So let's now do what we did before. We're going to use the Qt client. In memory, we're going to have a dense encoder that will create the dense vectors of the documents. And we're going to create a collection using the dense encoder embedding size. And we'll upload all the documents. It will take a few seconds. And we have all our documents there. And we're going to search it in a very similar way to the way that we searched before the dense index. We have the dense encoder, and we search this index with the dense query. And here are the results. So we already saw those documents. They are different documents because this is a semantic search. And here we have ID 15 and ID 4. So you can expect the same documents to appear, but different orders and different scores. Now, once we have those two results from the dense index and from the sparse index, we can merge the results. And the way to do it is to put all the documents together and to attach the score, the dense score and the sparse score to each one of the documents. So now we have a list of documents and a list of scores. We can calculate a weighted score from those two scores. We're going to normalize the scores for each one of them. And then we're going to create some kind of a weighted score with some alpha, where we give only 0.2 to the sparse scores and 0.8 to the dense scores. And we'll have a single score to both of them. Then we can check what are the top documents. So documents 15 and 4 and so on, with the merged score from those two dense and sparse scores. Now we can take our top document and do what we did before, call the generation part using the OpenAI, GPT 3.5, and we'll give it the search results from the hybrid search. And here is the response. We're going to get a good reply based on the improve in the retrieval that is based on this hybrid search option. Next, we're going to use those two results in our next notebook, where we're going to have a bit more sophisticated merging method using re-ranking.